Okay, so this is a video talking about how to compute the line integral over a vector field. Okay, now let's first define two things. One is line, one is a vector field. So line is defined by r sub t which is given by xt yt in 2D space. Okay, and also we define a starting and ending, assuming that we have a parameterized form of this line. We also have a starting point and ending point, which is represented by xt0 and yt0, and ending point defined by xtf and ytf. So the right hand side we should draw the curve of the line in the 2D space. So we have a starting point and ending point, and it's a curve, it's a line. It doesn't mean the straight line. Okay. The vector field, the second one is vector field. The vector field defines, as we can understand, vector field defines the vector for every point in the field. So this one basically defines any point. For example, I here use a couple of red points over here. This red point over here to define the vector. This is what I've defined by this v. For every point, this vector field will define a vector associated with that. You could have defined more with this vector point. So the line integral over the vector field is defined as integration of the v. This is still the v, and dot product with respect to this dr sub t. So this is a short chain, which means this is an integration of the vector field and a short change of my vector or the line. Okay, I integrate from t0 to tf. Okay, so pay attention to here. We have here must be a dot product. Must be a dot product, because otherwise we cannot do a regular product since they are all vectors. Okay. Now, how do we interpret the physical meaning of the line integral over vector field? Okay, so one example that we can interpret the vector field is to consider this v as a field that will define the force at any point. For example, if we use v dot xy to represent the force applied to a point, okay, any point in the field, so the force also defines two things. One is the direction, one is the magnitude, basically. So the integration of t0 to tf v xy dot drt can be interpreted as the total energy when moving along S. That's because each one, for this one, this one represents the force applied at any point, okay? And the drt represents, oh, I'm moving along that point. I move very, very tiny little bit to see how they'll create energy. Because if you only move a very tiny little bit, your v will almost be the same for that tiny little bit. That's why this will define energy for a very tiny little bit of intervals, and this one can be represented by v x y dot ds. Okay, of course this interval is very small, so you can pick not ds, dr t. So this is t has to be a point, like any point over here, because they are really close. You can just use anyone to represent the force. We consider constant force basically, and this is the travel distance. Okay, direction and distance and direction. Okay, so with that being said, we can go back to actually rewrite this form in a simple way, because this one is a little bit hard to compute. We have a d of a vector, right? It's better to compute the scalar integration in this form. So the key thing we have to remember is to just replace a couple of things. So replace what x we have and y we have by xt and yt over here. Okay, so here xt and yt are defined by the lines, okay, by the line s. And also we write the dr sub t by x dot t and yt. We just compute the derivative, because this is dr t is dr t and dt times dt. This is what comes out. This is just the it's just the gradient of my r sub t, which is also called a tangent vector. Okay. Now by doing this, we just compute this one will be just function of t. We compute dot product, which is also function of t, and we just integrate everything over t, which should be computable. Okay, now here's a simple example how we compute this. So here we assume we have this the line S represented by r sub t given by t and t squared plus 1. Okay, and t starting from 0 and 1. my vector field is defined by y and x squared. Okay, so now that my goal is to compute it from t is 0 to t is 1. Okay, starting ending point, I have v x y times d dot product dr sub t. Okay, now we have to replace x by xt. Okay, this by xt and this is by y sub t. So this x and y all defined. X and y, they both defined in my r sub t, basically. Okay. Okay, we're doing integration t 0 doesn't change. It's still from 0 to 1. I drop the t, just use 0 to 1. So this is v dot x and y. So what is xt? Xt is basically the first one. This one defines the xt. This is y sub t. The first one xt, second is yt. Okay. So xt is just t. So it's xt, right? Y is, we'll just do this way. So we just directly replace it by this. So this is y, vxy is by y and x squared. Y is a yt, okay. And this is xt basically squared. Times drt dot product. Drt is r dot t, which is just x dot t and y dot t and dt. Okay, so that's it. Okay, now just replace by the actual function of xt and yt. So yt is t squared plus 1 and xt is t, but here's t xt squared, so it's t squared time x dot t. X dot t is xt is t, so x dot t is 1. So x dot t, y dot t here is this guy, is t, the derivative of t squared plus 1 over t, so which is 2t times dt. So integration 0 1 with dot product is just the product of first entry of each vector, right? So it's t squared plus 1 times 1, so it's still 1 plus t squared times 2t, okay, dt. So this is just replaced by 2t to the cube. Okay. So integration of each one individually. So the integration of this one will be just the first one, t squared will be just t cubed divided by 3. The integration of 1 will be just t. Integration of 2t cube is 2 times 1 over 4 times t to the 4. So this will be just 1/2 basically. And then you value that as 0 to 1. Okay, so it will be 1 cube is 1 divided by 3 plus t is 1 plus 1/2 times 1 to the 4th is still 1. So drop it and minus 0. I don't have minus this one. So this will be just 1/3 plus 1 is 3 to the 4th plus 1/2, which is 6 over 8 plus 3, so 6 over 11 over 6. Okay, so this is how I compute the line integral over the vector field.